Okay, we begin the whole series with the lecture entitled Quantum Crystallography at Extreme Conditions, Necessities and Pitfalls, delivered by Piero Macchi. The second lecture today will be presented by Roger Johnson from UCL London and is entitled Charge Density Analysis and the Fundamentals of Magnetic Superexchange. Piero is one of the best known members of our community. Got his master's degree with honors in 1994 in chemical physics at the University of Milano, PhD in 1999, also at the University of Milan, with a thesis on electron density studies at low temperature crystallography of organometallic compounds. Then he defended habilitation in 2009 in chemical crystallography at the University of Bern on structural investigations of soft bonds. After the first period of scientific career at Milan University, Piero went for a postdoc and worked under supervision of Professor Finkrep Larsen at the University of Aarhus. Next, Piero worked as a researcher and got a permanent position as professor at the University of Milan. Then Piero moved to the University of Bern in Switzerland, where he got in 2009 permanent position as associate professor and the group leader of the chemical crystallography research group at the Department of Chemistry and Biochemistry. In 2018, Piero returned back to Italy, becoming associate professor at the Department of Chemistry, Materials and Chemical Engineering, Politecnica di Milano. And since 2020, he's been associated researcher at the Center for Nanoscience and Technology at the Italian Institute of Technology. Piero is co-author of XD package, probably the most common computer package people use in the field of electron density investigations, and also co-author of PolarBear, a program to compute distributed atomic polarizabilities. Piero published more than 150 papers, and he co-authored modern charge density analysis and quantum crystallography, and delivered more than 70 lectures at different conferences. He's been successful mentor of more than 20 PhD students and young researchers. So Piero, the screen is yours.
Thank you. Thank you, Christoph, and thank you, Paulina. I hope you can see the presentation, because now your faces disappear from my screen. Can you see?
Paulina?
Not yet. How about now?
Yes, now.
Yes.
Okay. There is some delay between Milan and Warsaw, probably. So thank you very much. I'm really honored to inaugurate this series of lectures. And I hope that this will be just the beginning of a very interesting and an appealing series of presentations, including also the one that comes after mine by Roger. So I'm not going to say more about where I'm staying now, because you can see it's not Springer time though in Milan as well, so it's not exactly the landscape I can see out of my windows now. But let's go directly to the point. This lecture is the first in this series, so let me say just a few words of what is the field of quantum crystallography, is at least as the one that we perceive right now, because maybe part of the audience is completely new to the community. So quantum crystallography basically brings together two names. One is crystallography, which is a science, the science that investigates crystals, their structure, and here in particular we are interested in electronic structures of crystals, and their properties, including properties that do depend on the on the quantum theory. And quantum mechanics is the paradigm that we use for the interpretation of small particles or fundamental particles like electrons, and that cannot be explained otherwise with the laws of the classical physics. So we put together the two things, and here we deal with quantum crystallography at high pressure. So we have to define even a little bit what is the scope, how the two fields overlap. Now, with the quantum crystallography, for sure, one is interested in the description of chemical bonding, for example, by means of some of the functions that we are used to deal with, like electron density, wave function that could be calculated, spin density, in case we have magnetism involved, spatial dynamics of atoms in crystals, and then a series of tools that do allow us to analyze the features of the chemical bonding. Now, all this is still valid, but simply we put the chemical bond under pressure. And of course, the deal here is to try to investigate what are the changes induced by the pressure itself. High pressure is not a particular tool to analyze those features, but it is a tool to analyze the differences between what is done normally at ambient condition and what is present at high pressure. Pressure is an energy density, which means that if you apply more pressure, you are able to manipulate matter more. So if your pressure is relatively low, I mean low compared to the standard point, which is of course the ambient pressure, what you are expected to modify are the weaker interactions in between molecules, and so to change, for example, the packing of molecules in crystals, which is basically within the field of polymorphism. So you can observe phase transitions or changes anyway of the intermolecular packing. If you do apply a little bit more pressure, then you are able maybe to modify also the inner bonds in a molecule. So and the chemical bonds that held covalently the atoms together. Or you may be able even to induce the presence of new bonds and allow the molecules inside the crystal, or the ions, or the individual atoms, it depends of course on the kind of material you're starting from, in order to react and to link them in a different way than before. If you do apply even more pressure, you are able even to change the inner cores of the atoms and changing, for example, important properties like the conductivity, so that you know that basically all matter, if put under high pressure, sufficiently high pressure, would become metallic. But we have also some kind of surprise, which is that some metals do become non-metals at a very high pressure. Now, we can put on the left side standard phenomena in the lower part of the pressure regime, and more interesting phenomena on the right part. But unfortunately, when we deal with data quality, we have exactly the inverse, because data quality is definitely better when we do not apply too much pressure, because applying pressure, you may induce some strain, some microstrain on the crystal, which initially may simply damage a little bit the crystallinity. But if you insist on non-hydrostaticity, you may even break those crystals, and so maybe lose a single crystallinity. And if you apply even more pressure, maybe you end up with some inhomogeneity in the sample, so that you may have part of the sample which has reacted, for example, and part which has not, which becomes even progressively more complicated to analyze. Therefore, high quality is definitely against high pressure, but interest is for going to high pressure. Now, when we deal with quantum crystallography, we are mainly interested in X-ray diffraction from crystals. And now the kind of problems, issues that we are facing right now when trying to determine accurate electron densities from crystals squeezed at very high pressure are very similar to the problems that our predecessors in the early 70s were facing when trying to determine electron density at ambient condition, at ambient pressure condition at least. One of them is certainly the motion of the atoms inside the crystals. If they move too much, you can't see them properly. You can't see the electron distribution properly, so you have to lower the temperature. If you want to realize some kind of sophisticated modeling, you need to have more reflections measured, and particularly high angle reflection, because in that way you can certainly fix with a high accuracy the position of the atoms. Otherwise, it's impossible to determine very accurately also their density properties. Of course, the measurement must be very accurate, because we are going to detail very tiny modifications from a pure distribution of spherical electron densities, which is of course nonsense, but it's good enough to refine most of the crystal structures that are published in the Cambridge Structural Database on a yearly basis. Of course, we want to minimize all kinds of errors, in particular absorption or extinction. We are, however, quite lucky, because nowadays we can take advantage of all the developments occurred in the past 20, 30 years, especially in the field of multipolar modeling, in the field of transferable aspherical atom modeling. This is more recent with respect to the multipolar, and of wave function calculation, which is even more recent. But when I say recent, I mean in the last 20 years, more or less. Let me just, because this is also the introductory lecture in this series, I have to go also and explain something that for the those who are new, completely new to the field, would become otherwise too difficult to understand. And I apologize with those who are expert, because of course I will not, I will just say something that they know very well. Anyway, for example, the multipolar expansion of the electron density is simply a way to try to describe the electron density of a molecule or a crystal by expanding basically what you can calculate from the exact wave function of the system. For example, if you have the hydrogen molecule, you know that the wave functions simply coincide with just one bonding orbital, at least within the approximation of the linear combination of atomic orbitals. But even in such a very easy example, the situation becomes complicated when you go to the electron density, because you have an orbital which is simply the sum of two spherical orbitals, like the 1s orbitals of the two hydrogens, but you have to compute the square, basically, of this function. And this produces a problem, because in terms of electron density, you end up with some terms which are certainly one-centered, so center either on one or on the other atom, and some which are two-centered, so they come from both atoms, and they do produce some kind of problem in the modeling. Now, if you want to do an electron density expansion, basically you want to reproduce this electron density by fitting a series of multipoles centered on each atom that try to approximate at best that electron density. So, for example, by taking two monopoles, then some dipoles, especially the one maybe along the bond direction, some quadrupoles, and so on. So you can do this expansion eventually up to a very high order in order to really describe the electron density. Now, the point is that even though you are dealing only with the electron density produced by spherical atomic orbitals, you cannot use just spherical density terms, because they would not be enough in order to describe the exact electron density. Here is the residual electron density that you would find if you do apply just a monopolar term to each of the two hydrogen atoms. Of course, in the hydrogen molecule, there is no charge separation between the two atoms, but still, the density terms cannot be just spherical. Well, if you add also the dipole to your description, you decrease the difference and you improve your R factor, meaning that you are approaching to the, let's say, exact electron density distribution. And if you do apply also the quadruples, then you clean up more or less your residual density map and you go toward a more accurate model. Of course, you should go on if you want to reach really an R factor of 0, which means a perfect match between what you want to model and your model. This kind of model is called the multipolar model, and more sophisticated is that you describe the atomic electron density in terms of core electron density, then valence electron density that could eventually be expanded or contracted, depending on the parameter kappa that you see in this formula, or the extended multiples that also can be expanded or contracted. Now, important is that this is an atomic electron density, and the total electron density is the sum of all these atoms. Therefore, in the diffraction space, the structure factor of your system is simply the sum of the atomic form factors, but of course modified by their position. So tuned by their position, which gives a phase to the overall structure factor, and importantly, also attenuated by a so-called thermal factor, which is the depending on the displacement of the atoms from the equilibrium position, you have an attenuation of the scattering power of the atoms. So what we need normally is to try to deconvolute properly the atomic thermal motion from the atomic electron density, and the best way is to lower the temperature. If you want to do this kind of model, you need certainly to go to high resolution in order to collect more reflections, because you need more reflections in order to calculate and refine all the parameters that you have included in this model. You need a data completeness, otherwise you may be biased in the definition of all these variables. And of course, you need highest possible accuracy, because you're dealing with very, very tiny deviations from a pure spherical atomic electron density, and therefore any error in the measurement is quite dramatic. What are the pitfalls? You may have correlation among parameters, and of course you may create some artifacts because of some error in the measurements. More recently, a number of databases, and here we have also one of our chairperson today who has been quite involved in trying to use a series of atomic aspherical form factors, for example, calculated or determined experimentally from a series of molecules collected in different crystal structure or calculated theoretically, and then using those rigid aspherical form factors in order to refine better structural models. The alternative is to calculate individually one atom in a given molecule that is sufficiently representative of that atom type, and then assembling all the possible invariant atoms. Or otherwise, one could calculate an entire molecular electron density and then refine exactly the parameters coming from that electron density. Alternatively, instead, one can try to refine coefficients of a wave function. In reality, refining a coefficient is very complicated, and it was a strategy actually abandoned in the past. Now, the most modern ways to do that is trying to minimize a particular functional which is constructed in such a way that you reproduce both the energy of the system and the similarity of your diffraction pattern with the experiment, the calculated diffraction pattern with the experiment. So if you minimize those two things, you have on one end the classical variational principle from the quantum mechanics, and on the other end you have the classical resemblance of the crystallographic data to the measured intensities. There are alternatives to this, which are the X-ray atomic or X-ray molecular orbital models developed, for example, by Tanaka, or more recently even a spin resolved kind of X-ray atomic models. Now, in this kind of models, there is a much bigger intervention of the theoretical calculations, which may help a little bit in the reducing, for example, the need for the high resolution. Although we will see that anyway, you need high resolution in order to fix properly the atomic positions. You still need very accurate intensity, you still need data completeness, although in a way the correlation among parameters when you do refine one of the wave function is more difficult to assess. So it's more difficult to understand exactly how much correlated are the parameters, so how lower is the precision with which you can certify your wave function. Anyway, here is just a schematic representation of all the arsenal that we have available. Well, there are even more methods, and under these names or these acronyms, you may find several declinations that, of course, I have no time to explain today. But basically, our goal is to go towards the true wave function. But of course, this is something we don't know, we can't know, so we can only try to approach with those kind of models which are more density-based or more wave function-based models, and try to approach as best as we can the experimental evidences that do depend on the wave function. Now, not only we have an arsenal of models, but we also have an arsenal of tools to analyze the chemical bonding. One of the most diffuse one is the quantum theory of atoms and molecules. I'm not entering in the discussion of all these quantities, but basically the quantum theory of atoms and molecules is based on a topological analysis of the electron density. If you have also a wave function model, you can even expand the arsenal of the available, because you can go and determine exact density matrices. You can calculate more localized, more strictly localized atomic or molecular orbitals. You can calculate some more functions like the electron localization functions, the electron localization indicator. You can derive more energy-related quantities, and in particular, all the energy densities. And therefore, you can do also some kind of spatial analysis like the natural bond order analysis, or all kinds of valence bond type analysis. Anyway, we are dealing with high pressure. So while all the tools that I have described so far have been developed starting from more than 20 years ago, although of course the development is continually ongoing. Only 20 years ago, there was the very first attempt to determine somewhat precise and accurate charge density from crystals squeezed at very high pressure. And this was done on a mineral, the stishovite, which is an high pressure form of silicon dioxide, which is, as far as I know, not stable in ambient condition, and it transformed back into quartz. It was studied up to 50 gigapascal and with some kind of multipolar model, but actually using only the monopoles. And if you remember a picture I've shown you before, the monopoles are maybe not enough to describe entirely the situation of an atom which is deformed aspherically. They were trying to develop a model, but here we see the residual electron density, and each of these lines is actually reproducing a residual of 0.2 electron per cubic Armstrong. So you can see that at the silicon position, for example, the residual is huge. But it was the first attempt, and we're talking about 50 gigapascal, which is a pretty high pressure, and so this attempt was extremely important. The same author, or some of the same authors, have proposed also later on a similar kind of charge density study, but based instead of a maximum entropy method, which is one of the methods very much diffused in crystallography to determine and refine crystal structure, but can also provide information about the electron density. On another inorganic salt, the potassium niobiate. Then 10 years later, at the Madrid Congresses, two posters or one poster and one lecture actually reported first attempts to refine a more sophisticated model for the charge density of organic molecules at high pressure, or anyway, organic salt at high pressure. One was from Francesca Fabiani and Birger Dietrich, who tried to apply one of those transferable spherical atomic models, so keeping rigid multipolar model and using high pressure data collected for a kind of standard resolution, so normally intended only to refine the crystal structure. The same meeting, we have presented instead the first multipolar refinement, although it was very much incomplete at that time. It was on a salt of piperazinium and hydrogen oxalate. Here you see a picture of the hydrogen oxalate. But unfortunately, this is not the residual electron density map. This was actually the deformation density map. So the difference between the data collected and the collection of spherical atoms, and normally you should see residuals in the chemical bonds, and here you see only in one, the carbon-carbon bond, actually some residuals. So this multipolar refinement, although successful because it was converging and giving even a relatively good R factor, was not complete at all, and the main reason was the lack of completeness in the data. We could only collect about 30% of the data up to a resolution of slightly better than 0.5 Armstrong, which is, let's say, the standard that you need in order to do a charge density refinement. Here I want to explain more in detail what is the problem. Now, if you have a normal diffraction pattern, this is just one plane reconstructed for alanine. Probably you don't see too much, it's a little bit low in color, but ideally, you can collect all the reflections, so you see equally spaced a number of spots. And if your diffractometer is good enough, you can collect all of them. But if you do that, applying pressure, and so putting your crystal in one of the diamond anvil cells that we have seen at the beginning of the seminar, then unfortunately, you can only collect a little portion of this diffraction. For example, these two portions. This is, in fact, what you can collect on that crystal. And the biggest spot you see on your right screen are the diamond. So the diamond that I use as anvils in order to apply the pressure, of course, are perfect and beautiful crystal, and they do diffract, and they do diffract well. But you're not interested in them. You're interested in the tiny spots that you see. So this is one of the reasons, the problem of data coverage. In a recent paper, Chonen and Macchi have proposed a way to optimize orientation of the crystals inside the diamond anvil cell in order to obtain the highest possible completeness of data, depending, of course, on the kind of radiation that you use and depending on what is the resolution that you want to achieve. For example, 0.83 Armstrong is the standard resolution recommended by the IUCR in order to collect enough data for a classical standard crystal structure determination. Whereas the opening angle of the diamond anvil cell, it is defined in different ways, but the way in which they have defined is this one. So it's a alpha is the semi-angle of this aperture, so 35 means that in reality you collect 70, and 55 that you collect in reality 110, maximum 110 degrees. And you see immediately that, of course, the kind of radiation, molybdenum and silver are two of the most common radiation sources that one can use in laboratories. They do allow you to achieve some kind of good resolution, but this depends very much on the diffraction symmetry. For those of you who are not crystallographers, all the symbols on the here on the left of these pictures are the Laue symbols, or the Derma-Mogen symbols, sorry, for the symmetry classes of the diffraction, the so-called Laue classes. And the top one, the -1, is the triclinic, so the lowest symmetry, and the bottom one is the cubic, so the highest possible symmetry. With the cubic, you can reach 100% of completeness, but with the triclinic, you can't, of course. This is, in a way, what you could imagine for a standard crystal structure determination, but if you want to do something like charge density, you're not happy with that kind of resolution, you want more. And in particular, for the molybdenum or the silver, you need to collect at least up to a theta of 45 for molybdenum and 34 for silver. This is theta, so 2 theta would be, of course, the double of this number, in order to achieve a resolution of 0.5 Armstrong. And here we have the development of this, depending on the opening angle of your duct, which, according to that definition, cannot exceed, of course, 90 degrees. And only for the Laue class -1, which is of course the worst one. All the others are quite better than this. But let's see what happens. I mean, if you want to use silver radiation, which has the shortest wavelength, so it's the best one in order to obtain higher resolution, then anyway, an opening of 40 degrees is pretty insufficient for the purposes of a refinement of a charge density model. And instead, the resolution of, so the opening angle of 60 degrees is much better, but again, you don't reach the full coverage. If you have higher symmetries, of course, the situation is a little bit better. Okay, but now let's come to, there is an additional problem, which is you may be happy to maximize that number, but in reality, the problem is that sometimes you also need to maximize the redundancy between reflections, because if one of them is, for example, measured very close to the border of the cell, you're not exactly sure that you are measuring it exactly or partially shadowed. And in that case, of course, the intensity is reduced by a number that you cannot absolutely estimate. So you need some redundancy, but redundancy is against completeness. So if you are redundant, you must abandon a little bit of your completeness. So it's a compromise that you have to choose. And redundancy, it's important here, doesn't mean just precision. It's not just free measuring the same reflection many times. It's measuring equivalent reflections in order to obtain some kind of more accurate measurement of the diffracted intensity. Here, one of our best example is this bis-carbonyl annuline, an organic molecule. And annuline is an aromatic molecule because of the number of pi electrons in the system, but is not highly or strongly aromatic because it's not exactly planar. It was studied by Riccardo Destro more than almost 30 years ago, actually, because as a series of tests of these molecules in order to determine the aromatic characters, and it was studied accurately in terms of charge density. Now, we decided to go for this structure because not only it was a very good crystal, but actually it has a very interesting phenomenon. If you apply pressure on it, although starting from a situation where all the chemical bonds are symmetrically disposed with respect to the symmetry of the molecule, which is of course lower than the symmetry of benzene, which means that basically that the two resonant electronic configurations basically play the same role, and they are exactly 50-50. By applying pressure, you start instead localizing one of the two electronic configuration. In this particular case, the blue series of bonds become shorter than the red one on average by applying pressure. And which means that you are changing something. And if you remember my very first slide, you are changing something not only in the environment of that molecule, but inside that molecule, which means you change chemical and covalent bonds. So it was a very nice test to try. You remember that one of the second problem I mentioned was the temperature. You cannot do very good electron density measurement and modeling if your atoms are moving too much. But luckily, pressure has a good advantage. Even though we measure it at ambient temperature, the compression is such that it reduces the available space for atoms to move, because it basically confines the atoms in smaller volumes, and therefore the atomic displacement parameter becomes much smaller. And there is a kind of connection between temperature and pressure. So the atomic displacement parameter, so the movement of atoms inside this molecule at a pressure of about 7 GPa, it's similar to the movement of the atoms at ambient pressure, but at low temperature, 120 Kelvin, which is a kind of highest limit for doing accurate charge density studies. So what we did was to use a very short wavelength in order to maximize the possible resolution. We didn't use, because at that time, especially the panoramic cell were not yet so developed, so we used a cell with a relatively small aperture, but we used 2 crystals in order to maximize the completeness. 2 crystals, of course, in different orientation, coupled with a very small focus. So clearly we measured this not at home laboratories, but at synchrotron stations where you can really apply microfocus. The data quality was guaranteed by the low absorption due to the high energy adopted. And as I said, the pressure is doing, in a way, the job of the low temperature. Okay, this is just to show how it looks like normally when you have a diamond anvil cell in front of your crystal with all these spurious peaks that you don't really want, and they damage, of course, the quality of your diffraction. Now, of course, what we could model was a multipolar model. We could model an X-ray restraint wave function, and we could test everything against the periodic density functional theory calculations that, of course, have the advantage that they can be applied and can be performed to as high pressure as you want. Now, the localization of the partial, at least localization of the double bond character became clear, especially if you go and see the valence density maps. Here you see the valence density, and you clearly see that there is a tendency to localize one of the 2 possible series of double bonds, something that becomes very obvious if you go to the at 50 GPa, but there, of course, we only have the theoretical prediction, but there it becomes obvious that the double bond character has localized in one of the 2 possible series of double bonds. This was also demonstrated by a kind of valence bond X-ray restraint wave function, where the 2 electronic configurations were tested, and while at ambient pressure you can't really decide that one is more probable than the other. At higher pressure, at least at 7 gigapascal, you see clearly the predominance of one against the other. Here is just to show that the residual electron density, albeit larger than what you normally can obtain at low temperature in an ambient condition, was anyway distributed normally, which means that the model you have refined was the best you could really obtain, and the least bias that you could really obtain, despite, of course, all the complications. Here I'm comparing also results of the multipolar against the X-ray restraint wave functions. The residuals and the R factors are extremely similar, because the 2 models eventually are quite similar in describing the data. Obviously, these data, these parameters are much higher than you normally obtain from experiments in ambient ambient pressure conditions and low temperature. There is no way, of course. Then some progresses very recently. Our chairman has published another mineral, in this case grossular, which is a calcium silicate, by applying pressure and testing multipolar refinement on it. This is not a molecular crystal, therefore it's more complicated to do X-ray restraint wave functions, but you can do, of course, the multipolar refinement. And just to connect to the next lecture before concluding, I want to introduce you some species, some materials that we have investigated at high pressure, which are extremely interesting for their behavior. And these are networks, metal organic networks based on copper pyrazine, which is basically defining the framework of this network, whereas some anion like BF4 minus are included in the holes. And by applying pressure, you are basically forcing against the Jahn-Teller axis, which is normally distorted, of course, for the copper 2+. This is a kind of standard for this kind of material. And therefore, while compressing, you're basically compressing along the Jahn-Teller distortion, because this is the softest bond in the structure. Now, what happens when you do this kind of study is that you reduce your Jahn-Teller distortion direction or the bonds along the Jahn-Teller distortion direction down to a limit of the non-Jahn-Teller distortion limit. Here we have a copper with an halide along that direction, and you progressively reach the limit of the non-Jahn-Teller distortion. And now it's interesting because when you reach that, you have now a competition between the two possible electronic states of the metal, the one in which you have the magnetic orbital lying on the copper and the pyrazine, and the one in which instead the orbital has rotated and is now aligned in another direction. And because we discussed early on about non-hydrostaticity, it's interesting that depending on the hydrostaticity or non-hydrostaticity of the medium, and of course in the second case on the orientation of the crystal, then you may produce different kind of phases. In all of them, anyway, at a certain point, you have a change between the magnetic exchange along the copper pyrazine network layer, which is the one where the magnetic orbital is lying at ambient condition, and the one perpendicular, which is instead the one that becomes progressively more involved as the pressure is increased. Now, just to go to this, will be shown and discussed probably by Roger, because this is a similar kind of study, but instead with copper formiate instead of copper pyrazine. And let me go to a summary of what we have learned in this half an hour of lecture. So we can do accurate electron density modeling at high pressure. We can do calculations of X-ray restraint wave functions at high pressure. Still, there is something to work on for spin density or magnetism, because it's more complicated to obtain those kind of information, as well as for the non-classical crystal dynamics. Then if we have all the functions that that comes from a normal quantum crystallographic study, then basically your arsenal of quantum chemical topology and chemical bonding analysis is working, and you can apply it, and therefore retrieve information about the chemical bond squeezed under high pressure. Very last slide about necessities and pitfalls and what we can expect next from this kind of studies. Certainly, using the more modern DACs with the highest aperture is an advantage, and this allows one to use, for example, silver K-alpha radiation for doing this kind of studies, therefore in the lab. So you don't necessarily need to go and use the synchrotron radiation, although of course if you can use an even shorter radiation and all the other benefits of synchrotrons, you can obtain better data. Redundancy and completeness also take some kind of advantage of these DACs, but again, one has to study. Not necessarily the highest completeness must be your goal when you do plan the strategy, because not all the reflections plays the same role. So one has to be careful. The pitfalls are hydrostatic limits. Of course, the pressure in transmission medium are those that you use in order to apply the pressure and transform the force applied on the diamonds into pressure on your sample, and they lose hydrostaticity relatively early in the pressure coordinate, along the pressure coordinate, and this of course is a severe limitation for any kind of very accurate study. You can still obtain very good structures, but the more accurate ones are probably lost. And as I've shown you, however, it's exactly at that position that maybe most of the species become interesting and they show some very interesting effect. Do we need low temperature? Possibly not. Okay, because the pressure itself is compressing enough. Okay, and I just want to acknowledge a number of people. I'm not going to read all this list. And of course, I thank you for the attention. And I thank again, Christoph and Paulina for this kind invitation. And sorry if I spoke for 5 minutes more than expected.
Thank you very much, Piero, for this really excellent lecture. so which is now open for questions and comments. Yes, do we have Jean-Michel? One moment.
I am not able now to see the chart, but okay, yeah.
Okay. Let's see the comments. These are congratulations so far.
Probably we have to start from
Piero, there is a question from Hansbert. How do you know that on compressing you don't approach a dynamical JT scenario?
Yes, of course you can't say. This is clearly a very good point. You don't know because there is no complementary kind of technique at the moment. So what you would observe from the structure could be in fact just an average, and you can't exactly know.
Okay, there is another question from Uli Engler. Let me. Yes, so Uli is asking, can we be sure in the MOF case that the motion limiting effect of high pressure is equal for all moieties?
No, clearly there is a difference between the framework and gas molecules, or in that case are ions inside the channels, because of course the ions inside the channels are moving much more than the rest of the framework. So it cannot be. So the picture I've shown, in which you have a correlation between the temperature and the pressure in order to reduce the atomic displacement parameters, may not hold in the case of the coordination networks. Clearly, there will be a difference between the network and gas molecules, or anyway the extra framework molecules.
Okay, thank you. And we have another question from Hansbert. Paulina, can you enable Hansbert to ask the question himself, maybe? Because it looks like will be nice discussion.
So I think the question from Hansbert is about the delta.
Yes.
So the differences in the mean square amplitudes along the bond distances. Well, first thing to say is that those figures that I've shown were calculated electron density, so the electron density was not coming from the experiment in that case. So just to make sure that this is not misunderstood. Secondly, the most interesting scenario is what happens when we have a non-hydrostatic compression, because in that case you induce a phase transition from tetragonal, which is the phase stable at ambient conditions, into a monoclinic, and you basically break the tetragonal axis, because you basically force against one of the two directions which are equivalent, and when this pressure becomes non-hydrostatic, then one of them becomes unequal with respect to the other. Now, the problem in terms of doing an analysis of the displacement parameters along those directions is that actually there is a disorder, of course, which is induced by this phase transition. Therefore, the accuracy with which you know those parameters is insufficient to do any kind of accurate analysis. That's the main problem.
Uh, e- oh,
Daniel.
Daniel, yes. So maybe I can read. I agree that maximizing the completeness may not yield the best strategy, as individual reflections might have different leverage. Do you have any idea how one could evaluate leverage of individual reflections in order to plan the most optimal, the optimal experiment?
Yes, this is something I would like to suggest you, in fact. I think you should have to put a kind of penalty function for each reflection. Penalty means giving a kind of weight to each reflection, which is based on the leverage, for example, with respect to a multipolar model. This is easier because if you do it with a X-ray wave function, it's more complicated because it's not so easy to calculate the leverage. But the leverage for multiples is easy. So every reflection may have a weight. And now what you should do in your program would be not to maximize the number of reflections, but to maximize, let's say, or to minimize the penalty of this function, or maximize the overall weight, in order that you do collect not the largest number of reflections, but overall the most important reflections.
Mm-hmm. Okay. If I could just have a short comment, really there is quite a big problem with reference data, in my opinion, because we do not have very reliable neutron results for substances under pressure. And so it's difficult to compare whether we are getting reasonable results or not. So this kind of combined studies, high pressure studies, X-ray and neutron would be really very valuable just to get a feeling how reliable are, for example, thermal motions of atoms.
Yes. Sorry, I was reading again 2 comments
Next.
of Ansbeth and Daniel. So Ansbeth is suggesting that this kind of done by Danitz and Saylor, I think he is referring again to the leverage, I guess, by weighting high resolution more. Yes, in the past there was an even more naive strategy, which was that of collecting at high angle only those important reflections based on a prediction made from a model refined at low angle. Even more naive than the one which is suggested now by Ansbeth. And of course, this is something that one could do also for the high pressure. Basically, one can try to suggest. Now, the additional little problem is that one thing is being sure that you can measure those reflections, and one thing is, which is always possible if you have a diffractometer in ambient condition, you can measure every reflection. The limitation at that time, of course, was the time, because only point detector were used. Another thing is what you can do in the dark, because in the dark you may try to orient the crystal the way you want, but the precision of this orientation may not be the right one, and so this is a little bit problematic. But anyway, yes, what I have suggested is not something particularly innovative; has been already thought before. And Daniel, I think, says that of course the leverage may change with the pressure. Yes, of course, this we can't avoid.
And Dietmar is asking for explanation of the difference between a duck and a panorama duck.
Panoramic duck, yeah. Well, of course, now there are a number of equipment that enable basically to do almost everything, including being able to etch the crystal not from the diamond but from perpendicular to the diamond, so going through the gasket. Of course, if the gasket is made of a material which is transparent enough to be done, and therefore you increase enormously the possibility of collecting the data. So apart for the opening angle, which was of course the suggestion I gave before, there is also this possibility to basically rotate the duct with respect to the direct beam. And this is, of course, opening even more. I'm not so sure if this was contemplated in the paper by Daniel, maybe not. And so it would even give more possibility of higher resolution. Of course, one always has to pay attention, however, with accuracy. So you don't want to increase your resolution and your completeness at the expense of the accuracy in the measurement of your reflections, because otherwise, I mean, you increase on one side, but then you lose the most important thing, which is the intensity itself. So it's always
yes, there's a question from Anya Makal. Can the panoramic duct be mounted on an in-house diffractometer at all?
I guess yes. I've never used on a home diffractometer, but I guess yes. Well, of course, mounting a duct is always a little bit complicated, apart for the very standard ones, which are now more or less just a little bit more indirect than the normal goniometer heads. All the other kind of ducts, especially those that are moved by membrane compressed by the gas, are of course more indirect. But we have done this also on in-house diffractometers, so it's not impossible.
Mm-hmm.
I think the more, if I can go on with this comment, I think the most important thing is the kind of energy basically that you can reach with a synchrotron that allows you, of course, to go. In the case of I have presented, we went to 0.31 Armstrong of wavelength, and this is probably unbeatable in in-house. But of course, if in-house the kind of experiment you can reach the necessary resolution, then I think everything is doable. Mm-hmm. For sure, I guess not less than silver radiation. That's the point.
Exactly. Yeah. Okay. As I do not see more comments, more questions. Thank you very much, Piero, for this excellent contribution.